I'm an internal student, I'll be the only one presenting. I am from the Giuseppe school located in Somma Vesuviana in Naples. And today I'm going to talk about our project, which is What You Can. In particular, we want to focus on its visibility, our research work, and the development. Here in the bottom left, you can see the newest logo of our school, while in the bottom right, you can see the future of school. It used to be a convent, then it got renovated and school since 1963. So today I'm going to talk about our project, which is What You Can. And as I said before, we want to focus in particular on its visibility, the research work we made, and the development we intend to perform. At the beginning of our project, we started as regional apprentices. Then, thanks to the hard work and to the art study, we finally become data scientists. So, about the feasibility, we intended to perform to realize a building project, in particular this robotic hand, able to replicate human hand movements and to physically determine situations. By only using components we have in our school, in our laboratories, we use the Arduino board, the Arduino Nano board in particular, then we use the servo motors, flexor sensors, and this hand is fully 3D printed. And most of all, these apps must be able to be implemented and integrated by the students in the next year. So, about the project, this hand has four command fingers. Each one has 3 phalanxes and also a thumb, a normal human hand. And this thumb has 2 phalanxes and also a major movement capability. Each finger must be able to perform articulated movements, and the whole hand must be able to adapt to the shape of the object. And most importantly, this hand must be driven by a human being in real time. So, at the beginning of our project, we realized that if we started from scratch, from nothing, this would have been practically impossible. So we made a research work, and thanks to this research work, this brought us to 3 products, and 1 product on the market, and 3 products now from the scientific community, 3 proposals from the scientific community. So now I'll talk about the 3 proposals from the scientific community around the world, and 1 product now available on the market. The first proposal from the scientific community is from the Laval University in Quebec, and it's really simple. You can see on the right, this is a project on 1 finger. This is really similar to a human hand in real life. It's made up of 4 command fingers, each one able to perform position movements. The second proposal from the scientific community is from the San Diego University in the United States, and this is quite more complex than the previous one, because it focuses more on the concept of synergy, since the fact that each finger is independent and it's controlled by its tendon. The third proposal from the scientific community is from the Italian University of Bologna, the UB Hand 3, and this is the only proposal that provides the possibility to have an exoskeleton to each finger. There are 3 different solutions for this proposal. A one-piece solution, in this case, we use the same material for the 3 different parts of the hand, so for the phalanxes, hinges, and tendons. The second solution is also a one-piece solution, while we use elastic material for phalanxes and hinges. While the third proposal is a completely differentiated one, so we use 3 different materials for the 3 different parts of the hand. And this makes the project way harder to realize, but at the same time, we gain the maximum flexibility. The only product from the market we want to talk about is model Michelangelo from the German Auto block. And we want to focus in particular on this hand because it's really simple, it's quite cheap, and reproduces different hand gestures and allows you to perform 7 different grip combinations. We want to focus in particular on this product, since the fact that our project is really similar to this one, that means inspired by the Auto block model Michelangelo. And this is a picture that shows the working phase of our hand. It's still not completed. In our hand, you can see it incorporates a mechanical structure made by the palm, the articulated fingers, and the thumb. Then an electromechanical actuation system made by which consists of 7 motors in the lower back of the hand. Then there is a control system, the Arduino board, not shown in the photo, and then the analog sensors, the accelerometers on the control cloth. This is a picture that shows the finally completed project, fully 3D printed. This is the control circuit, the Arduino Nano board, and then the control glove with the sensors attached to it. So the most important key points are highlighted on the right. This hand is largely controlled by a human in real time, thanks to the control glove. Each finger is independent, it is fully 3D printed in PLA plastic. So let's focus now how our hand actually works. We talked about flexor sensors. These flexor sensors are placed on the control glove. And the variation of the flexions varies the resistance. This variation of resistance is then controlled by the Arduino and converts it into a degree between 0 and 180 and sends it back to the servomotors. This makes the finger move into the side position. Before using the hand, we always have to perform an auto-calibration routine because without it, the hand wouldn't be able to work properly. This is a block diagram that shows how the data is made during the operating on the hand. So the input is carried out by the flexor sensors, the control system is carried out by the Arduino analog board, and then the output are the actuators. So let's talk about our fingers in our hand actual move. We talked about the servomotors before. The servomotors are connected to two nylon threads which slide inside the finger. And these nylon threads can be seen as the tendon in the real life human hand. So the servomotors, by rotating clockwise and anti-clockwise, makes the tendon be pulled and pressed, so this makes each finger be closed and opened as we want. So I said before that the hand is fully distributed. This is true. It was not a lie. And this was fully distributed PLA plus significant organic derivation, and we use the 3D printer we have in the school, which is the 3D rack. This is the electronic structure, the most important part of the whole project. It's made up of 4 parts: the supply block, the control circuit, power circuit, and the signaling circuit. The supply block is merely just a 9-volt power supply that gives out a current of 2 ampere, which is enough to power up all the servomotors, which are in the lower part of the hand. Then the control circuit is the Arduino board. I said that we use the Arduino board. We could have used another kind of board, another model, but we tended to use the Arduino board, which is really small and it's big enough to meet all of our needs. The power circuit has been realized by using the microchip 7806, which is used to stabilize the voltage from 9 volts to 6 volts. And this would have taken the temperature way higher than the low temperature, which is 135. So we had to use an instant we have in the electronic laboratory. Then, the last part of the electronic structure is the signaling circuit. This is the part of the project that gives out the feedback to the user. And it's made up of 3 different LEDs. A red one, a red one, a yellow one, and a green LED. The first LED shows the presence of power supply. So if the hand is power supplied, it should be on. Then the yellow and the green LED gives out the feedback to the user. I said before that before using the hand, we have to perform an auto-calibration routine. And the yellow and the green LED tells the user when the auto-calibration routine has started. Two kinds of auto-calibration routine. With the closed hand, so when the yellow light turns on, you have to close the hand. And when the green light turns on, you have to open the hand. After this routine, this light should be off, and you should be able, and if it's power supplied, you should be able to use the hand properly. This is the control block we have been talking a lot, and you can see the flexor sensors on each finger. So this the variation of the flexion of these sensors varies the resistance, but the resistance must be controlled in this central Arduino, and must be translated into converting it from resistance to a variation of voltage. And this is carried out by the sampling circuit. You can see this is the whole circuit scheme shown in the picture. This circuit has been realized by using the software AbleCut, and in which you can see the whole circuit scheme of the complete project. So here's the Arduino. Here are each finger connected to the analog input port of the Arduino. So this is the management software. The management software is probably the most important part of the project. Without it, it wouldn't work. It is written in the Arduino language. This language is really similar to Java and C++. And as every Arduino code is made up of 3 parts. The first part, we declare all the variables we need. While in the second part, which is the setup block, it is run just one time during the operating of the hand. And the setup part, we perform the famous auto-calibration routine we're talking about. It asks the user to close the hand, then open the hand, turning on and off the LEDs, and then after the setup block, there is the loop part, the loop block of the code, which is run forever until there is power supply. So in the loop block, we scan for the value of the flexor sensor, convert it into a degree between 0 and 180, and send it back to the servomotor, which moves the finger up X degrees. So this makes the finger move in the such position we are controlling with the glove. This is the logo of the Arduino language. And this shows how the hand works. You can see the teacher is the user now in Italy, and you can move. Each figure is independent from this animation. You can see. So it's completely independent, as I said before. Close, you can open, close, whatever you want, which finger you want. So, as I said before, another most important key point of our project is that it must be able to be implemented and integrated by the students in the next year. And this is because probably this project is not going to catch dust on the shelf. We want to develop it. And the future developments we intend to perform in the future are here shown in the slides. So, first of all, we want to make a prosthetic plant entirely 3D printed and add some low-cost sensors, making it affordable to most people. And second of all, we want to be able to create something able to substitute a human limb, and to also add a tactile perception, which is usually only present in something really expensive. Another development we intend to perform is to substitute the Arduino board with a Raspberry Pi board. And that's because, in particular, when you add the 3 version, because this version allows as the Wi-Fi and Bluetooth capability, and this makes us able to control the end without use of any wires, so